As we have previously agreed that link scheduling is necessary and it has an impact on the overall network capacity. But the scheduling itself is governed by certain assumptions and constraints, which are mostly called the radio model or the wireless model of the channel. We'd look at an example topology to understand that. The references are by Anurag Kumar and Kenneth Calvert. First, we understand that the problem of link scheduling is a trivial problem if it were a single hop communication scenario. Because in single hop wireless communication scenario, the sender and the receiver have to agree on simplex, half duplex, or full duplex mode of communication. But the scheduling problem is a serious problem if it is a multi-hop wireless network environment. In wireless multi-hop environment, the topology discovery has to be the previous step before scheduling can take place. And for that, certain neighbor discovery and neighbor power strength algorithms are incorporated. Once these discovery and power algorithms are used, then the whole map of the topology is available to nodes, either in a distributed manner or in the centralized manner. So each node actually has a part or whole of the picture of the network, that is a graph with number of nodes and edges. These edges are of course wireless links. These edges could be directed or undirected. By directed we mean if node I sends data to node J, it means it's directed. And if node J sends data to node I, it is directed. But if node I and J share a wireless channel that they both use for sending and receiving, we can call it undirected. If the transmissions are sent from I to J, it means J is going to be the receiver, which must have the right kind of receiver sensitivity, and the signal to interference ratio has to be significantly higher. Typically in wireless environments, the signal to interference ratio is of the order of 10 dB. Now we look at the scheduling constraints. The first one is that the edges in the whole network topology can, or in other words, may or may not be grouped into subsets. If the edges cannot be grouped into subsets, it means it's a very closely knit topology and these nodes are in very close radio range of each other, and it is a kind of situation in which a node once transmits, all the other nodes receive. So the neighbor density or the average number of neighbors per node is very, very high. If that's the case, then the scheduling constraint is the strongest, and it means at one instance of time only one node can transmit because all the others would be listening. But if the edges can be grouped together into subsets, that's a good news. What it implies is that edges in the subset can be activated in the same slot. For instance, if you are using slotted aloha kind of mechanism, in that case, simultaneous transmissions could be activated in the same time slots with no collisions. The receiver in each edge would be decoding from its respective transmitter because it is not receiving any interference or transmission from the unwanted sender. Of course, the next constraint is the number of slots availability. It is determined by number one, the scheduling discipline. Number two, the overall order, also called the beacon order of the communication session. For instance, if the overall communication session is going to be, say, 1 minute, and if the total number of competing pairs is, let's say, 6, each pair is going to have 10 seconds worth of time availability. But if the total time that could be slotted is 1 hour, then correspondingly, each node each node pair is going to get around a minute. So when we talk about the time availability, when a slot is available, then each node is going to send to its respective destination a packet, because sending more than a packet means that it is going to transmit packet which collides with its own transmission within the same time slot. Let's look at the sample network topology. Here we see that we have 6 nodes and their connectivities are shown in here. If we were to create independent sets, we can see that in set S1, 1 and 2, 5 and 6, and 3 and 4 can have simultaneous communication sessions. In the second set, we have nodes 2 and 3 and 1 and 5 which can simultaneously transmit, and the subset S3 is also obviously saying the same. So it means we can actually create a network in which all the nodes are simultaneously transmitting without their transmissions colliding with each other.